to our very first lesson in Basic Calculus. This is your teacher, Miss Jen, and it's my pleasure to guide you in understanding this course. Today we shall talk about the limit of algebraic functions. At the end of the lesson, I hope that you can illustrate the limit of a function using a table of values and the graph of a function. Distinguish between the limit of a function in x as x approaches a and f of a. Illustrate the limit laws and apply the limit laws in evaluating the limit of algebraic functions. That includes polynomial, rational, and radical function. Get it on! First, let's understand the expression. The limit of f in x as x approaches a certain value. F of x is the function under consideration, and a is the value at which x gets closer and closer to, but never touches it. If we are asked to evaluate this expression, it means that we have to find out the resulting value of the function under consideration when the variable x is replaced by a value that is closest to a. Let's say f of x is equal to x plus 1 and x approaches 3. It can be written as the limit of x plus 1 as x approaches 3. We can understand this clearly by using the graph of the given function. We put an unshaded dot on the graph of x plus 1 at a point on the graph having an abscissa of 3. Notice that this point will have coordinates of 3, 4. Let us trace the graph. From the left, as our pen approaches 3, the value of f of x becomes closer to 4. As we trace the graph from the right, we can see that as x approaches 3, the value of f of x also gets closer and closer to 4. Therefore, we can conclude that as x approaches 3 from either left or right, the value of f of x gets closer and closer to 4. Hence, we can write that the limit of x plus 1 as x approaches 3 is 4. From the graph, we have seen that we can approach a point having an x-coordinate of 3 either from the left or from the right. This time, let us make a table of values of the limit of x plus 1 as x approaches 3 from the left. Let's say we consider x equals 2. We are going to replace x by the value of 2. In that case, the function will have a value of 3. When x is 2.5 or 2 5/10, the value of f of x would be 3 5/10. Whereas, if we have 2 9/10, replacing x by 2 9/10, the function will have a value of 3 9/10. Now let's say we have chosen a value that is very much closer to 3. Like if we have 2 point followed by 8 nines, we will have f of x is equal to 3 followed by 8 nines also after the decimal point. Okay. From here, we can see the trend that as x approaches 3, the value of f of x approaches to 4. Therefore, the limit of x plus 1 as x approaches to 3 from the left is 4. This time, let's approach x equal to 3 from the right. Let's say we choose 4 as the value of x. Now replacing the variable x by 4, we would be able to have 5. If we have x equals 3.5, replacing the variable x by 3.5, we will get 4.5. If we will have a number that is much closer to 3, like 3.2, replacing the variable by 3.2, we will have 4.2. If we have 3.0001 as the value of x, we would be able to get f of x equal to 4.0001. If we choose again a much closer value to 3, like 3.00000001, we would have f of x equal to 4.00000001. Now look at the trend as the value of x approaches 3, the value of f of x approaches 4. Therefore, we can say that the limit of x plus 1 as x approaches 3 from the right is also 4. Since the value of the limit of x plus 1 as x approaches 3 from the left is equal to the limit of x plus 1 as x approaches 3 from the right, we can say that the limit of x plus 1 as x approaches 3 is 4. Now let us consider the function g of x in which the function is defined by x squared minus 1 if x is less than 2 and x plus 2 if x is greater than or equal to 2. We are asked to evaluate the limit of g of x as x approaches 2. To visualize the function, we graph the piecewise function. Now we draw an imaginary line that separates the values of x at the left of 2 from those values of x from the right of 2. Then we get the value at which the function approaches 2 as x approaches 2 from the left. In other words, we will consider the values of x which are less than 2. In this case, we will focus on the graph of f of x equals x squared minus 1. Looking at the graph, as x approaches 2, the function gets closer to this point, having coordinates 2, 3. This means that the limit of x squared minus 1 as x approaches 2 from the left is 3. This time, let us consider the values at which the function approaches 2 as x approaches to 2 from the right. Hence, we will consider the values of x which are greater than 2. With this, we shall focus on the graph of f of x equals x plus 2. Looking at the graph, we can say that as x approaches 2 from the right, the function gets closer to this point, having coordinates 2, 4. This means that the limit of x plus 2 as x approaches 2 from the right is 4. Recall that in order the limit will exist, the limits of f of x as x approaches a from the left should be equal to the limits of f of x as x approaches a from the right. Since we got different values at which the function approaches 2 as x approaches to 2 from the left and from the right, we can say that the limit of g of x does not exist. Let's verify our answer using a table of values. Note that you can choose any value for x as long as it satisfies the conditions. Looking at the set of conditions, we will consider the function defined at x is less than 2. Hence, we will be evaluating the limit of x squared minus 1 as x approaches 2 from the left. Have you arrived at the same values just as what I did? From the table of values, we can conclude that the limit of x squared minus 1 as x approaches 2 from the left is equal to 3. Now let's evaluate the given function considering the values at the right of 2, which are the values greater than 2. So we get the function having a condition x greater than 2. Hence, we will have the limit of x plus 2 as x approaches 2 from the right. Study the given table of values. Use your scientific calculator and verify the values that you see. Looking at the table, we can conclude that as x approaches to 2, the function approaches to 4. Therefore, the limit of x plus 2 as x approaches 2 from the right is 4. From this table of values, we can clearly see that the two sides of the limits when evaluated has approached different values. Remember this: if the limit of f of x as x approaches a from the left is not equal to the limit of f of x as x approaches a from the right, then the limit of f of x as x approaches a does not exist. Now let us consider the limit of the square root of x plus 3 as x approaches to negative 3. Notice that the radicand should not be equal to a negative number such that this function will exist. So, for example, if x is negative 4, we would be able to have negative 4 plus 3 when simplified will give us negative 1. So in this case, the given function does not exist if we will have a value that is less than negative 3. So in order to solve for this, we have to redefine the given expression. Now, since we cannot consider values of x which are less than negative 3, we have to redefine the given expression as the limit of the square root of x plus 3 as x approaches to negative 3 from the right. Since we know we cannot select or we cannot consider the points at the left side of negative 3. Using our graphing application, we would be able to have this graph. So it also shows that we have a one-sided limit. So we can just evaluate this limit as the limit of the square root of x plus 3 as x approaches to negative 3 from the right. Now, if we will trace the graph from the right as x approaches to negative 3, the value of f of x approaches to 0. So therefore, we can say that the limit of the square root of x plus 3 as x approaches negative 3 from the right is 0. Is the limit of f of x as x approaches a always equal to f of a? Now let's consider this given. Evaluate the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches to negative 5. Now evaluating this at x equals negative 5, we would be able to have 2 times negative 5 raised to the second power plus 11 times negative 5 plus 5 all over negative 5 plus 5. Simplifying the numerator and the denominator, we would be able to arrive at 0 over 0. Remember that division by 0 is undefined. In this case, we can say that we have arrived at an indeterminate form of the function. Okay. However, if we will apply factoring techniques, we would be able to cancel out some factors. Let's see. If we will simplify first the radical function before evaluating, we would be able to have, instead of 2x squared plus 11x plus 5, let's express the numerator in factored form. So 2x squared will have a factor of 2x and x. Then 5, we have 1 and 5. But we need to have a middle term of 11x. So we place 5 here. Then we place 1 here. So having checked this, 1 times x is x, 2x times 5, we will have 10x. Combining that, we will have 11x, which is equal to the middle term. Now, we copy the denominator, which is x plus 5. Okay. Then we have x approaches to negative 5. We can already see that we can cancel out the factor x plus 5. So in this case, we are just going to evaluate 2x plus 1 as x approaches to negative 5. Evaluating the given function 2x plus 1 at x equals negative 5, we would be able to arrive at 2 times negative 5 plus 1, we will have negative 10 plus 1, we will have negative 9. So therefore, the limit of 2x squared plus 11x plus 5 all over x plus 5 as x approaches negative 5 is negative 9. Now, before we proceed to the limit laws, I would like you to remember the following key points. The limit of a function f is a number L that the values of f of x approach as x approaches a certain number a. It is written as the limit of f of x as x approaches a equals L if it exists. Second, the limit of f of x as x approaches to a from the left is the limit of f of x as x approaches the number a from the left. Meanwhile, the limit of f of x as x approaches a from the right is the limit of f of x as x approaches the number a from the right. They are also known as one-sided limits. Now, in order that the limit will exist, make sure to have this one to arrive at a single number when we evaluate the given function from the left and from the right. So the third concept would be the limit of f of x exists and is equal to L if and only if the limit of f of x as x approaches a from the left is equal to the limit of f of x as x approaches a from the right be equal to L. Now, we can evaluate the limit of a given function, y equals f of x, by using either tabular method or graphical method. And lastly, the limit of f of x is, as x approaches a, is not always equal to f of a, just like the last example that I have given you. Now let us consider the following limit laws in order to generalize our application of the concept of limits. Now, the first one is the limit of a constant. The limit of c as x approaches a is equal to c. So for example, we have the limit of 2 as x approaches -1 is just equal to 2. Now when we have the limit of x as x approaches a, then we can have a. Just like if we have the limit of x as x approaches to -1, we can just evaluate the given function at x equals -1. Hence, we will arrive at -1. So the limit of x as x approaches to -1 is -1. Now what if we have a polynomial function? If f of x is a polynomial function a and a is a real number, then the limit of f of x as x approaches a is just equal to f of a. So for example, we have the limit of -2x plus 7 as x approaches 1 can be evaluated using or through this solution. We can have -2 replacing x by 1. We will have -2 times 1 plus 7. Simplifying this further, we will have +5. So the limit of -2x plus 7 as x approaches 1 is 5. But what if we have the limit of a product of a constant and a function? This rule states that if we have a limit of c times f of x as x approaches a, this can also be evaluated using this expression c times the limit of f of x as x approaches a. For example, we have the limit of 2 times the quantity x squared minus 3 as x approaches 1. We can have 2 times the limit of x squared minus 3 as x approaches 1. We copy 2, then evaluate the given function at x equals 1. So we will have 1 squared minus 3. Simplifying further, we will have 1 minus 3. Then we will have 2 times -2. Therefore, we will have -4. Hence, the limit of 2 times the quantity x squared minus 3 as x approaches 1 is -4. Now, what if we have the limit of the sum or difference of two functions? So for example, we have if f of x is negative 3x and g of x is equal to 12x minus 1, find the limit of f of x plus g of x as x approaches to 0. So in this case, we will have the limit of negative 3x plus 12x minus 1 as x approaches 0. Then we evaluate the given function at x equals 0. So we will have negative 3 times 0 plus 12 times 0 minus 1. So we will have 0 plus 0 minus 1. When simplified, will just be equal to negative 1. Therefore, the limit of f of x plus g of x as x approaches 0 is negative 1. What about if we have a limit of a product of two functions? Just like in the rule, if we will have f of x negative 3x and g of x still 12x minus 1, we are asked to find the limit of the product of f of x and g of x as x approaches to negative 1. So we evaluate that. Okay, it's like the limit of negative 3x times the limit of 12x minus 1. Okay, as x approaches to negative 1. Then we evaluate the given function using x equals negative 1. So we will have negative 3 times negative 1. Then we will have 12 times negative 1 minus 1. Simplifying, we will have positive 3, while this one would be negative 13. Multiplying that, you will have negative 39. What about we have quotient? Now let's consider the same set of functions, and we are asked to find the limit of f of x over or divided by the g of x as x approaches to negative 3. So we can just have the limit of negative 3x as x approaches to negative 3 divided by the limit of 12x minus 1 as x approaches negative 3. Then we can just evaluate negative 3 times negative 3 divided by 12 times negative 3 minus 1. Simplifying further, we will have 9 over negative 37. Now what if we have the limit of the nth power of a function? So with this, let's have an example. Let's say we have the limit of the square of 2x minus 1 as x approaches 1. Applying the same strategy, we evaluate the given function at x equals 1. And remember that it's raised to the second power. Then we will have 2 minus 1. 2 minus 1 is 1. Square that, we will have 1. Therefore, the limit of the square of 2x minus 1 as x approaches 1 is 1. Now this time, let's have the limit of the nth root of a function. So let's say we have the limit of the cube root of 6x minus 27 as x approaches 0. So replacing x by 0, we will have 6 times 0 minus 27. Then we simplify, we will have 0 minus 27. Simplifying further, we will have the cube root of negative 27. And we think of a number that when multiplied by itself 3 times will give us negative 27. That number would be negative 3. So therefore, the limit of the cube root of 6x minus 27 as x approaches 0 is negative 3. Aside from the limit laws that we have just discussed, we also have laws governing infinite limits. Let's take a look at the first set. If r is any positive integer, then we have two conditions. The limit of 1 over x raised to r as x approaches 0 from the right is equal to positive infinity. Second condition, the limit of 1 over x raised to r as x approaches 0 from the left is equal to, there can be two possibilities, positive infinity if r is even. The second one would be negative infinity if r is odd. Now, understanding this further, if x approaches 0, if we will evaluate the given limit through f of a, take note that we will have an indeterminate form. Okay, but as you can see here, the value of x approaches to 0. It cannot be really equal to 0. So hence, we would use the graphical method instead of having an evaluation of the given limit at f of a. Now, let's take a look at the first example. If we will have the limit of 1 over x cubed as x approaches to 0 from the right, using our graphing application, we would be able to see that as we approach, or as the value of x approaches to 0, the value of f of x increases without bound. Therefore, we can say that the limit of 1 over x cubed as x approaches to 0 from the right is positive infinity. Now consider the second example. The limit of 1 over x squared as x approaches 0 from the left. Let's have a graph. If we will have this graph, as you can see, we will have from left. We will have to trace the graph from left to the right. Okay, so we trace this graph. Now, as the value of x approaches to 0 from the left, the value of the function increases without bound. So we will have positive infinity. Now take a look at our rule. Does it adhere to the rule? Now, since we have r equal to 2, r is an even number, therefore we will follow this one. Okay, now let's take a look at the limit of 1 over x squared as x approaches to 0 from the right. So we have from the right we trace, then as x approaches the value 0, the graph increases without bound. Therefore, the result would be, for the limit of 1 over x squared as x approaches 0 from the right is positive infinity. Now let's consider the second set of laws about infinite limits. If a is any real number and if the limit of f of x as x approaches a is equal to c, where c is a non-zero constant and the limit of g of x as x approaches a is equal to 0, then we can have 4 possible outcomes. So if first condition or first possibility, if c is greater than 0 and g of x approaches 0 through positive values of g of x, then the limit of f of x divided by the limit of g of x as x approaches a is positive infinity. Second possibility, this time we are going to have through negative values of g of x. In this case, the limit of f of x divided by g of x as x approaches a is negative infinity. The third possibility will have this condition if c is less than 0 and g of x approaches 0 through positive values of g of x, then we will have the limit of f of x divided by g of x as x approaches a is equal to negative 8. Lastly, if c is less than 0 and g of x approaches 0 through negative values of g of x, we can evaluate this. The limit f of x divided by g of x as x approaches a is positive infinity. But these conditions hold true if x approaches a is replaced with either x approaches a from the left or x approaches a from the right. Now let's consider the given example. Let h of x is equal to the square root of 2 plus x over x. Find the limit of h of x as x approaches 0 from the left and the limit of h of x as x approaches 0 from the right. We have to choose among the 4 conditions presented a while ago. First, we have to determine the value of c. Okay, so take note, if we will have the limit of h of x, so that would be the square root of 2 plus x over x as x approaches 0 from the left. Evaluating this, we will have square root of 2 plus 0 over 0. Simplify further, we will have square root of 2 over 0. So, take note, our c is greater than 0. And we are considering that the limit goes through the negative values. So, in this case, we are going to use the condition, the second condition, which is if we have the limit f of x divided by g of x as x approaches 0 from the left, we will have negative infinity. Okay. Now, what if we have the limit of 2 plus x divided by x as x approaches 0 from the right? We know that it's equal to square root of 2 over 0. Now, c is greater than 0 and g of x is 0, but it goes through the positive value, then the rule states that the result is positive infinity. Okay, let's take a look using the graph. If we will have from negative values, so that would be this, our answer is negative infinity. So take note, the function decreases without bound. Now, on the other hand, if we have the limit of h of x as x approaches 0 from the right, let's trace. Take note that the function increases without bound. So It supports our answer that the limit of the square root of 2 plus x over x as x approaches 0 from the right is positive infinity. Okay, so as you can see, we were able to apply the given rules perfectly. Now this time, let's take a look at some laws governing limits at infinity. If n is positive integer, then the limit of 1 over x raised to n as x approaches to negative infinity is 0, while the limit of 1 over x raised to n as x approaches to positive infinity, we also have 0. So let's take a look at this example, the limit of 1 over x cubed as x approaches to positive infinity. Now, take a look at this. Since we are approaching positive infinity, that means we will start from the left to the right. So tracing this, we will have from to positive infinity. If left to right, so we will have this. We have to consider this. Okay, from left to right. Okay, going to positive infinity. Now take note that the graph is asymptotic to 0. Therefore, this is equal to 0. Now what if we have the limit of 1 over x cubed as x approaches to negative infinity? So negative infinity, right to left. Okay, so right, we consider this, we trace this, then take notes that it's also asymptotic to the x-axis. Therefore, this expression is also equal to 0. Now let's consider this given example in order to check what we have learned. Evaluate the limit of 2x minus 3 over x plus 5 as x approaches to positive infinity. The first thing to do is to arrive at an expressions which are similar to what we have seen a while ago, especially those in the rules. Okay, so in this case, we divide each term by x. So we will have 2x over x minus 3 over x all over x over x plus 5 over x. Simplifying further, we will have the limit of 2 minus 3. We can write this as 1 over x. Okay, as x approaches to positive infinity, then in the denominator we will have 1 plus 5 times 1 over x. Then applying the first set of limit laws, we would be able to have the limit of 2 as x approaches to infinity, positive infinity, then minus 3 times the limit of 1 over x as x approaches to positive infinity, all over the limit of 1x approaches to positive infinity plus 5 times the limit of 1 over x as x approaches to positive infinity. Now we simplify further, we will have the limit of a constant is always equal to that constant minus 3 times the limit of 1 over x as x approaches to positive infinity is 0. Okay. Then we have the limit of 1 is 1 plus 5 times the limit of 1 over x as x approaches to positive infinity. That would be equal to 0. So hence we would have 2 over 1 or simply 2. Now to support that using the graph, okay, if we will have to check on the limit of 2x minus 3 all over x plus 5 as x approaches to positive infinity. Take note, to positive infinity, this is the graph. Then we trace. Okay, as you can notice, the graph is asymptotic to 2. That strongly supports our answer a while ago that the limit of 2x minus 3 divided by x plus 5 as x approaches to positive infinity is really 2. Now let me remind you about the important key points on the discussion on the infinite limits and limits at infinity and the limit laws. Okay. Remember that we can evaluate any algebraic function, polynomial, rational, or radical function by using one or a combination of the limit laws. First, if f of x is defined as a polynomial function, then we can have the limit of f of x as x approaches to a is just equal to f of a. If f of x is defined as a rational function or a radical function, and a is in the domain of f, then the limit of f of x as x approaches to a is equal to f of a. However, if f of x is defined as a rational function or a radical function, and f of a is an indeterminate form, then we evaluate the limit of f of x as x approaches a by first factoring or rationalizing f of x in order to cancel out common factors between the numerator and denominator, then applying the limit laws. Okay, I hope you were able to attain all the objectives for this lesson. Illustrate the limit of a function using a table of values in the graph of a function. Distinguish between the limit of f of x and f of a. Then illustrate the limit laws and apply the limit laws in evaluating the limit of algebraic functions such as polynomial, rational, and radical. So again, that's our lesson for today. See you next time.